Welcome to the second part of multiple reaction system under the head of polymer reaction engineering. Now, before we proceed further, let's look at what we studied previously. We had gone through the concept of multiple reaction system. Under this head, we discussed about the parallel, series, complex, independent type of reaction system. Then we performed the quantitative treatment of product distribution under the head of single reactant system. Now, in this particular lecture, we are going to discuss about the qualitative treatment for two reactants in parallel, because this is one of the most common tool in all kind of reaction engineering concept, especially polymer as well as in the chemical reaction engineering concept. Then we will discuss about the quantitative treatment of product distribution and reactor size in parallel reaction system. We will discuss about the qualitative analysis of series reaction system. So, all these things we will try to cover in this particular lecture. Now, let us have a concept of a qualitative treatment of parallel reaction system. Now, there are two type of reactants, let us see. Now, to obtain the favorable product distribution in multiple reaction system having two types of reaction, most important factor, they are contacting pattern of reacting fluid and the combination of low and high reactant concentration of feed material with excess of certain components. Now, see, one thing is that you are having two different reactants and you are looking for a favorable product distribution. It is quite obvious for the economy of any kind of system. Now, if two type of reactants, they react in two different reaction pathway and produce two different products simultaneously, these can be represented as A plus B Kr, they are giving, that is the desired product, and A plus B Ks, they are giving the undesired product. Now, sometimes when we talk about these desired one and undesired one, people are always looking for the rate expression, and when we try to write the rate expression for the corresponding product of R and S, remember R we are representing as the desired one and S we are representing as undesired one. So, the rate equation for the desired one can be written as RR dt Kr Ca A1 Cb B1, and sometimes we may write like equation number 1. And if we try to write for the undesired one, then we can write Rs is equal to d Cs upon dt Ks Ca A2. This you can represent like equation number 2. Now, sometimes we may have to look into the relative rate of formation of product R and S, usually represented by SRS. So, this relative rate of formation of product R and S, now if we divide this equation 1 with equation 2, we may have this S is equal to RR upon RS is equal to dCr upon dCs is equal to Kr upon Ks Ca A1 minus A2 and Cb B1 minus B2. Now, this is my desired equation for the SRS, and let us represent this equation as equation number 3. Now, here we have to keep relative rate ratio SRS as high as possible to favor the formation of the desired product, because see, in the numerator we are having RR. So, therefore, we must maintain this ratio on the higher side. Therefore, following points usually decide when we have to keep the concentration of reactant high or low. Now, if A1 is greater than A2 and B1 is greater than B2, then keep both the concentration Ca and Cb high. Now, if there is the other possibility that A1 may have a greater A1 is greater than A2, then and B1 is less than B2, then you may need to keep Ca high and Cb low. Now, if A1 is less than A2 and B1 is greater than B2, then you need to keep Ca low and Cb high. Similarly, if A1 is less than A2 and B1 is less than B2, then keep both Ca and Cb low as possible. And sometimes one last option is there when A1 is equal to A2 and B1 is equal to B2, then Kr upon Ks ratio decides the product distribution. So, these 6 or 5 or 6 parameters and approaches, they decide about the favorable product distribution condition. Now, sometimes during the multiple reactions, you need to look into the contactic pattern of reactants in non-continuous operation with the combination of high and low concentration. Now, you need to go for various permutation and combination. You may have to keep your Ca and Cb high, you may need to keep Ca and Cb both low, and you may need to keep the Ca high and Cb low. Now, if you keep both Ca and Cb high, then added reactants A and B abruptly to the third container and mix them continuously. So, this is a usual protocol. Now, here you see that instantaneously you need to pour all these contents of A and B into another container or additional container. Now, if keep both Ca and Cb low, that is in this condition, then added reactants A and B dropwise, you can add all these things in a dropwise manner to the third container and mix them continuously. Now, if you decide to keep both Ca high and Cb low, that is in the third container, then you need to start with A and you need to add B very slowly. So, or in a dropwise. Now, this is usually this protocol decides about your product favorable conditions. So, sometimes you have to be bit choosy about these kind of protocols, and adoption of these protocol is extremely important for the product final product outcome or a final product distribution. Now, when we are talking about the contacting pattern, and sometimes we need to deal with the continuous operation with the combination of high and low concentration. Now, in that case, sometimes you need to design your own reactor battery. Now, there are again various combinations or various permutations are available for these kind of approaches. Now, if to keep both Ca and Cb high, then you may have either this type of a tubular reactor, or you may have this reactor battery where you are putting both A and B in the reactor, and then you can treat all around. Now, if to keep both Ca and Cb low, then you may need to have this type of recycle approach, and or you may have this particular type of approach which we discussed in previous slide. Now, if you are intended to keep both Ca high and Cb low, then in that case you may have this option that you can you can put or you can pour this B into this continuous fashion, and you may have multiple opening through which you can distribute the B all around this reactor, or you may have this type of reactor battery for making the product condition favorable. Now, let us have a look about the quantitative analysis of product distribution and reactor size in parallel reaction system. Now, the rate equations for individual reactions, they are required for the quantitative analysis of product distribution and a reactor size. Now, sometimes these poses various issues in the reactor geometry. Now, to overcome the difficulties in calculation of product distribution, we have to introduce two terms: instantaneous fraction yield, that is psi, and overall fraction yield, that is phi. So, you need to put these things into mind. Now, let us have a look about the instantaneous fraction yield, that is represented by this psi. Now, if there is a decomposition of a reactant A and psi represents the fraction of reactant, A disappearing and transformed into the desired product R at any instant. So, when we talk about this psi, the here psi is the function of reactant concentration, that is usually referred as a Ca. Now, it is called the instantaneous fraction yield of desired product R. So, if you recall that we are terming that A plus B, they are converting into R and S, where R is the desired product and S is the undesired product. So, this psi deals that how much fraction of desired product being achieved in the due course of a reaction. Now, this yield can also be defined in terms of a moles and a reaction rate of product and the reactant. Now, sometimes if we try to put this thing in a mathematical approach, then instantaneous fraction yield psi may be given as moles of desired product R formed during the course of a reaction divided by moles of reactant A, whatever reacted, and this represented as psi is equal to dCr upon minus dCA. Now, if Ca be the concentration of reactant A at any instant, and psi is the function of Ca that we have already shown in this equation, the concentration of A, that is Ca, and instantaneous fraction yield varies throughout the reactor's position. Therefore, there is a need for the introduction of a new term, that is overall fraction yield is always evident, and this represented by phi. This is the fraction of all the reactant A converted to the desired product. Now, this sometimes people may ask that why there is a need of this additional thing. The reason is that when you are moving from this station to this station, then the concentration of A may vary all around this reactant, and therefore, when we talk about, because it represents the instantaneous things. So, when obviously for the designing pattern we always look for the overall fraction yield. In that case, you need to have another function that is called the phi. So, this phi is the overall fraction yield. Now, this overall fraction yield is the average of instantaneous fractional yield of all the portion in the reactor. So, whatever portion you have discussed, it carries out all the information of the entire reactor system. Now, it is represented as at the outlet of the reactor, and the average of instantaneous fractional yield psi depends upon the flow pattern within the reactor. So, let us think in this direction, that like this is your reactor, and as I told you that instantaneous, the psi represents the instantaneous one, and sometimes it depends on the flow behavior or the flow pattern within the reactor. Now, if you are having any kind of say mixing protocol over here, then the psi may have more or a lower value. It may not be having the constant value throughout the reactor, and phi represents the entire segmentation. Now, mathematically we can write the psi as overall fraction yield phi, that is equal to all moles of desired are formed divided by all moles of reactant A reacted. Now, this may be represented as CRF, that is the R represents the desired component that is formed and F represents the formation. Ca naught, that is the initial concentration of A, and this is the final concentration of A. So, that is the phi, or this is CRF upon minus delta Ca, and sometimes it may represent the average of instantaneous fractional yield psi. Now, here these things Ca naught, that is the initial concentration of a reactant A, CAF, that is the outlet concentration of a reactant A of the reactor, CRF, that is the final concentration of desired product formed, and bar psi is the average value of all instantaneous fraction yield. Now, let us have a look about the product distribution profile. The product distribution profile and product distribution and a reactor size for plug flow and or batch reactor, they can find out with the help of overall fractional yield. So, that is why the overall fractional yield is quite important in all kind of reactor pattern. Now, let us have a look about this plug flow reactor first. So, for plug flow reactor, the concentration of reactant A changes progressively as it passes through the reactor length, which we have already discussed. The quantitative relationship of PFR you can write like this: phi p is equal to minus 1 upon Ca naught minus Caf integration of Ca naught to Caf psi dCA. Now, this phi p is equal to 1 upon delta Ca, Ca naught, Caf psi dCA. So, this is the relationship, the plug flow reactor. Now, let us have a look about for the mixed flow reactor. Now, there is a uniform mixing of the matter inside the reactor. Now, if you see the mixed flow reactor, now here this is the uniform mixing. So, you may experience the uniform product concentration CRF everywhere throughout the reactor. Therefore, psi remain constant throughout the reactor. So, if we try to write the equation, then we can say like phi m, for the m represents the mixed flow reactor. This is equal to psi evaluated at CAF. Now, sometimes you may be interested to find out the relationship between the overall fractional yield in plug flow reactor and mixed flow reactor, because the combination of these type of a reaction is again more common, and you may be interested to look the mathematical approach of these type of combination or the reactor battery. So, for the decomposition of the concentration of reactant from initial concentration which is represented as Ca naught to the final concentration Caf, and sometimes it may be represented as phi m is equal to d psi p dCA at CAF, and phi p is equal to minus 1 upon delta Ca, Ca naught to CAF phi m dCA. So, this is the equation which categorically reflect this particular relationship. Now, this equation is again useful in predicting the yield of another reactor system. Now, if the yield for one reactor system is known to you, then you can predict the another reactor system. Now, that is why these equations are quite useful. Now sometimes you may interested to find out the concentration of the desired product R formed in any type of reactor. Then you may require another set of equation that is represented as CRF is equal to phi Ca naught minus CAF. So this equation tells you that reactor is your any kind of a reactor. Now here the phi represents the overall fraction yield of either plug flow or mixed flow reactor. The value of the desired product may be find out by using this particular equation for any type of reactor. Now you can see here we have represented two figures courtesy from Levenspiel. This shows that the CR is formed for the different type of a reactor. Now here you see that the x axis represents the Ca and this is the Chi. Now you can see that in plug flow you may have you may experience this type of thing, and then mixed flow you may have this type of thing. So when we talk about the overall performance or overall things of any type of a reactor, in that case the plot of this concentration of a reactant versus Chi is always useful to give the proper reactor configuration or proper reactor battery designing. Sometimes this approach gives you again an idea that what is the best product distribution profile. Sometimes the plug flow reactor you may have over here, then you may have a mixed flow reactor you may have over here, and then followed by the mixed flow reactor followed by the plug flow reactor. So sometimes you need to carry out such type of evaluation, such type of a calculation to assess that which kind of reactor configuration is useful for your desired product distribution. Now these expressions whatever we discussed, they gives us give us an idea for best selection of contacting scheme and allow us to relate the product distribution from different type of reactors. Now there is one condition that should be satisfied before say we use these reactor or these relationships under the safe condition. One is maybe like in the parallel reaction, no product should have effect on the rate to change the product distribution. Now to test this, the product stream added to the feed and the verify that product distribution does not change. So you need to look into this particular approach while assessing this particular approach. Now so whenever we talk about the fractional yield of desired product R, this should be taken as a function of reactant concentration A alone. For more than 2 reactant, the fractional yield may be the function of one of the reactant consumed or all of the reactants. Now when we talk about the reactor configuration, and especially when we talk about the instantaneous or phi or Chi aspect, then selectivity is also very vital. Now this can be defined as the ratio of the rate of formation of the desired product to the formation of undesired product, and that is why it is sometimes it is called the instantaneous selectivity. Now this selectivity can be defined in terms of moles, as it is the ratio of the moles of desired product formed to the moles of undesired product form. Now let us give you a mathematical representation or a mathematical relationship of instantaneous selectivity. Now this SRS is represented as, that is the rate of desired product formed divided by rate of undesired product formed. Now sometimes people may look into the overall selectivity. Now overall selectivity is more common in the mixed flow reactor. So for mixed flow reactor, it can be defined as the ratio of exit molar rate of desired product to the undesired product, and we have to maximize it to favor the formation of the desired product. So if we try to write the overall selectivity for mixed flow reactor, the overall selectivity FR upon Fs, that is equal to exit molar rate of desired product R divided by exit molar rate of undesired product S. Now sometimes you may look into the batch or a plug flow reactor selectivity. This can be defined in terms of number of moles of desired and undesired product formed. So let us look for this one for batch or a plug flow reactor. The overall selectivity, that is equal to Nr upon Ns, and this is number of moles of desired product R formed divided by number of moles of undesired product S formed. Now sometimes we may need to look into the series reactions. Now this type of a reaction, the reactant is consumed to produce an intermediate product, which then further reacts with under the given condition to form another product. So in a layman's language, you may say that you are forming two products, and one product is in due course of time disappears to form the final product. So these reactions are sometimes called the consecutive reactions. Now if you see that there is this reaction, the chemical reaction, the reactant A is consumed with rate constant Kr to produce an intermediate R, which is further disappears or further react to form unwanted product, or sometimes represented as S with a rate constant Ks. So this is termed as the series reaction. When we talk about the mathematical representation of these series reactions, so the series reaction for the various component like decomposition of reactant A, then the rate of formation of intermediate R, or then rate of formation of unwanted product S is sometimes may be written as, like if you write the rate equation for the decomposition of reactant A, then it can be represented as Ra is equal to minus dCr upon dt, that is minus Kr into CaA1. Now if we write the rate of formation of intermediate R, then it can be represented as Rr is equal to dCr upon dt Kr CaA KSA2. Now if we write the rate of formation of unwanted product S, it is not necessary that entire R may get consumed in due course of time. Then for unwanted S, we can write Rs is equal to dCs over dt Ks CaA2. So this is the mathematical representation of these series reaction. Now let us have an analysis of qualitative approach of these series reaction. So for qualitative analysis of series reaction, we may treat the things in a beaker containing the reactant A with two ways. First way is that a beaker containing reactant A, and there is a homogeneous mixing of mixture in beaker, and the mixture is uniformly irradiated sometimes. Now at the start of the experiment, the only reactant A was present. Now when the light is attacked to the reactant and form the product intermediate R, with the next bit of light, both A and R will consume the light and convert into the product R and S respectively, right. So partially the R and significantly S. Now the concentration of the reactant A progressively decreases and the concentration of intermediate increases and reaches to a maxima value. After that, the concentration of reactant decreases more rapid than its rate of formation usually goes on increasing. Now here this is the graphical representation what we have discussed, that initially you may have the concentration of A on the higher side and there was no R and S, and progressively it goes on decreasing and sometimes you may have a very low value, and this intermediate goes on increasing and it reaches this maximum value, and thereafter it is having the tends to decrease. Now here this S, that is the unwanted product, initially it was having the it was having the 0 presence, and then over the period of time it gradually increases and it is having the tendency towards increase as long as the sufficient quantity of R and sufficient quantity of A is available in the reaction mass. Now let us talk about the second way. Now in the second way, let us take the small fraction of reactant A in a beaker and which is continuously removed and irradiated and sent back to the beaker. The flow rate of the side stream is not so much, so the total absorption rate is usually same in both the cases, but the intensity of absorbed light is usually greater in that case. Therefore, the reactant stream irradiated being completely converted into the product S. So, the reactant is removed progressively and the product is sent back to the beaker, accumulate there. So, the concentration of the reactant decreases and product is increased, while the intermediate formed is negligible in that particular case. Now, let us have a look about this thing. Now, here you are having the things inserted to this reactor, then they are sent back, and here you are irradiating the things and then you are making this particular cycle. Now, here you see that initially you are having the reactant A right on the top at time 0, there was no conversion, and then gradually it tends to decrease, and whatever are being formed due to this cyclic approach, it reduces over the period of time. Therefore, it is not having much concentration in the reactor mass, and the product S is continuously being increased in due course of time. Now, at last we take the things in a different way, that the yield of these the above two ways of reacting the beaker content, they are different, which represent the two extremes of possible operation. In the first one there is a maximization of the intermediate R, and then and in the second one with a small or negligible formation of R. In the first method there is a homogeneous content all the time and all changing slowly with the time, but in the second one the stream of a reacted fluid is usually mixed with the fresh fluid, fresh fluid. Now, therefore, we can conclude that the mixing of the fluid of a different composition is the main reason for the intermediate formation. Second is that the maximum intermediate is formed in the fluid of a different composition and stages are not allowed to mix. Now, at last if you wish to have further studies of this particular concept, especially series and a parallel, and what kind of configuration is useful, you may have a look of these references which we listed in this particular slide. Thank you very much.